Bismillahirrahmanirrahim. Assalamu alaikum, my dear students. How are you? Hope you will be fine and okay. I welcome you all into my today lecture. Today is our lecture number 44, Modern Physics, Unit 18. So in the previous lecture, I told you about the frame of reference where I told that it is a coordinate system where measurements are made. A coordinate system where measurements are made. A coordinate system where measurements are made, and then I talked to you about the types of the frame of reference, the inertial frame of reference, the non-inertial frame of reference. Then we went on towards the relative motion, and then in the relative motion, I told you about the absolute quantities, and the relative quantities are the relative motion. And I just want to, in order to study the special theory of relativity, I would like to tell you about, or to just to remind to you about the relative motion, which were a part of which was in class 9th, little bit introduction, and in class first year. So if you remember last time that is in those classes, a teacher told you that, for example, let us suppose let's see that if there are two cars, the car A, as you see, and the car B, like this one, and if the car B is moving with a speed of, let's say, 70 meter per second, and the car A is, this is car B, and the car A is passing the car B, crossing the car B with a speed of 90 meter per second. And then if you want to find the speed of the car A relative to the speed of the car B, that is a person who is measuring the speed of the car A in the B frame of reference, then to him the car A will appear is with the speed of 20 meter per second. So actually the car A is not moving with the speed of 20 meter per second, but it is the relative speed which makes the difference here. Similarly, when they are moving in the opposite direction, then the relative speed will be 140 meter per second. So keeping those things into our mind, we now move on to the special theory of relativity, which Einstein presented in, I think, in 1905. That in his special theory of relativity, his famous special theory of relativity consists of two postulates, and it is the outcome of the relative absolute motion and the speed of light. So it comprises on two postulates, The first postulate of the special theory of relativity, or STR, is that all laws of nature are the same in all inertial frame of reference. All laws, all laws of nature, all laws of nature, all laws of nature are the same, are the same are the same in all inertial frame of reference, inertial in all inertial frame of reference, in all inertial frame of reference, reference. And you know, I told inertial frame of reference is the non-accelerating frame of reference, right? That is the simple example I would like to tell you, that are, for example, let me more summarize this to you, that the laws of physics, the laws of physics, the laws of physics are invariant, are invariant in all the inertial frame of reference, in all the inertial frame of reference, frame of reference. This is the first postulate the spatial theory of relativity, STR. The example I would like to tell you that is on when you travel in a airplane, that, let's say for example, travel with a speed of 550 kilometer per hour, and then a copy for as it does when the plane is at rest. You wouldn't feel any change on this. A second example I would like to tell you that no physical experiment, even with light, is to determine our state of uniform motion, right? That the result of this is that no physical, that no physical, that no physical experiment, that no physical experiment, even even with light, even with light. Now, why I have chosen light as an example, I'm coming to tell you this in the next statement. To determine, to determine our state of uniform motion, or state of, our state of uniform motion, or state of uniform motion. What does this mean? That there is no experiment which can tell us about our state of uniform motion, that whether we is at rest or whether we are in uniform motion. So in our frame of reference, which is inertial, that no experiment can predict our motion. There is no way that we can do this thing. So what does this means in reality? The first statements summarize this, that there is no such thing as, there is no such thing, there is no such thing as absolute motion, as absolute motion. There is no such thing as absolute motion. Okay. So this is the first postulate of the Newton second law, the STR, the Einstein spatial theory of relativity, that the laws of physics are invariant in all inertial frame of reference. For example, if you are performing in an experiment in a frame of reference or in a coordinate system which is rest on the earth, for example, to measure the time period or to a simple pendulum, right? Beside other, ignoring other factors like the value of g, etc., if you are performing the same experiment in an aeroplane which is moving with a constant speed or which has a uniform motion, you will come across with the same result. So the laws of physics are invariant. The second important postulate is the limit on the speed of light, that the speed of light, the speed of light, the speed of light in vacuum, okay, which is 3 into 10 to the power 8 meter per second, or 300,000 kilometer per second, or 1,86,000 miles per second. So the speed of light, the speed of light is the same, the speed of light is the same for all the observer, for all the observer, for all, the speed of light is the same for all the observer, irrespective of either irrespective of either the same for all the observer, irrespective of either of either the source or the observer. The source or the observer is in motion, is in motion. Like, look here in this circumstances, what you notice here, you notice here that the speed of A with respect to B, that is the observer which measure the speed of A in the B frame of reference, produce different result than when they are at rest, or then when the speed that is the when the speed of the which the observer B calculates in the frame of reference of the B car is different when they are moving in the opposite direction. But this is not applicable to light. So whether the observer is moving, for example, if here is the source of light, and whether if the observer in B is moving or at rest, it will always measure the speed of light the same as 3 into 10 raised to the power 8 meter per second. So in vacuum, the speed of light is always the same, right? So this leads to some important results. There's limit on the speed of light, and that is what we will discuss in the applications of the STR. Applications of STR. Class, remember in your book, they did not derive any of the application. They only explain you the result of the application. The first application, A, is known as simultaneity of events. Simultaneity of events. B, time dilation, length contraction, and option that is in D, the mass increment. Mass dilation or mass increment. This is the events, these events is for usually observable for objects close to the speed of light, close to the speed of light. Okay, now let us explain the first principle, that what does the simultaneity of events. Now what does this simultaneity of events means? That this mean that the two events that are simultaneous, that are simultaneous that are simultaneous that are simultaneous in one frame of reference, in one frame of reference needs not to be simultaneous, needs not to be simultaneous in a frame of reference, in a frame of reference moving relative to the moving relative to the first frame of reference, to the first frame of reference. This is known as the simultaneity of event. For example, let us consider two frame of reference, right? That is the one, let we choose, for example, if we have like this, let's say that, let me explain you. For example, if we have a train, as you see, like this as I'm doing, right? Like this. And let us see, we choose the a compartment in the train, for example, like this. Okay, now this train, the train frame of reference is a moving frame of reference. Here we have the two frame of reference here. One, for example, there is an event carrying on in the, let I do it with this. Okay, here we have one, this frame of reference. Okay, and there is an event that is being carried out here, and one frame of reference here I would like to make. Let one is this frame of reference. Here, this frame of reference is at rest, right? That is at rest. And let us suppose, for example, its velocity is 0. Here, this frame of reference is moving and it has a velocity, some velocity v, right? Look, for example, that if there is, if there are two doors, for example, door 1 and let we have door 2. So here there is D1, here it is, there is D2 for the train. D1 and D2 are the two doors, right? Right at the center, there is a bulb, or here a lamp or a bulb, LED. There is light emitting diode. I will label this as LED. And the door are fitted with some photodiodes. Okay, the door are fitted with the photodiodes here, one photodiode here and one photodiode here. The LED is located right at the middle of the two door, and now there is an observer. The observer A is sitting somewhere here watching the situation. Here is the observer. This is observer A. Here we have another observer, and this is the observer B, right? The observer B is in the rest frame of reference, the observer B. Now, when the LED is switched on, the door will open when the LED is switched on, and the door will close when the LED switch off. So for the observer A, when the LED is switched on, when he switches on the LED, both doors open simultaneously. Both the doors opens what? Simultaneously. So the opening of the door simultaneously, because they are located at equal distances from the light source. The light travel at the same, arrive at the same instant for both doors. But this does not happen in the case of what? In the case of the B. For B, what is going to happen, that as the light source is traveling in this direction, right? It is traveling in this direction, right? So it is moving away from the door D1. So for the observer B, the door D1 will open at time later than the door D2, right? The door D1 will open when the door D2 already has open. So you see that this will notice two different things. This is this is known as simultaneity. That look, the event which occur at the same time here does not occur in the reference frame B. This is because of the result of the second postulate, right? That the speed of light is constant, universal constant in all frame of references. Okay, so this is known as simultaneity of events. There might be other examples. There might be other examples also that you may study well for your experiment. The next application here is the time dilation. Time dilation. Time dilation. And to be long story short, that is how one can travel into the future. Time dilation is that moving clock runs slow. Moving clock runs slow. Yeah, moving clock tick slow. Right? That is what does this means, that motion affects event. Motion motion affects event. That even time has been affected by motion when the speed is very high. That is the, I'm not going to derive this relation for you, right? But I will just directly write the equation and will try to explain it to you in a better way so that you can understand the things without derivation, right? Like this one. As you see, 1 minus v square by c square. Now I would like to explain it to you, that what are these things. This is known as T naught. T naught is known as the proper time, right? Or the proper time, it is the time which is measured by the observer in the rest frame of reference, right? That is the m proper time. That is called what? The m proper time. Now what is this m proper time? This is the time which the improper time, this is the time which the observer for example, let us suppose in the rest frame, which is the observer in the rest frame, that is which is the time, which is the time where which is the time the observer in rest frame of reference measure for an event that occurs in the moving frame of reference, moving frame of reference in the moving frame of reference, which the observer occurs in what? Measure in the moving frame of reference for an event that is the observer in the rest frame, measure an event which occurs in the moving frame of reference. Now that is the, here we have what this, let this v, that is This is the speed of the moving frame of reference. Speed of the moving frame of reference. Moving frame of reference. Moving frame of reference. And what is this? This is the speed of light. The speed of light. This is the speed of light, c, which is equal to 3 into 10 raised to the power 8 meter per second. Another important point which I would like to tell you is, long story short, to cut a long story short, this t, this time, this is known as relativistic time. Relativistic time. This is what I will call non-relativistic. Non-relativistic time. Non-relativistic time. This is called what? This is called the non-relativistic time. Okay. Now let us see here that the non-relativistic time, which is the time which the observer measures this, in a moving frame of reference, that is the observer who moves in the observer who is in the moving frame of reference, and he measure the time for an events that take place in the same frame of reference, that is the moving frame of reference. So this is what we call the proper time. And now let us see that why this all happens. This all happens, it is because of the fact of the speed of light is the same, or it is constant. It is not affected by any event. This is how the result is. For example, let us suppose that if you have two clocks, right? The two clocks, you have synchronized the two clock. Let's say the clock A and you have the clock B, right? And both the clocks are synchronized in a rest frame of reference, which is non-moving, right? Now, let us suppose, for example, the clock B is now located. The clock B is now located in a frame of reference which travels with 0.6 C, right? And that is the clock B is now on board. So when the frame of reference, this is for example A, and this is the frame of reference, let's say X, and this X dash or whatsoever you call, right? So when the clock B is returned back, then there will be a difference of time. This is known as the relativistic time difference. And now how this happens, for example, let us suppose you measure a time for an event. Let's say that time is, for example, 12 seconds, right? Yeah, let's suppose, for example, that the time you are measuring for certain event that finishes at 12:00 p.m. today, for example, right? Now when the clock B is on board, and when you return, for example, if the clock A show you the time, for example, let's say 12:08 p.m., then the clock B, when upon returns, wouldn't show you the 12:08 p.m. It will be less than this, means the moving clock runs slow. Now let us suppose, for example, as I told, the time difference for an event, it is 12 seconds, let us suppose, for example, right? So when the clock B returns, right? Yeah, when it measure an event in the moving frame of reference, for which takes 12 seconds in the rest frame of reference, then how much it will take in the moving frame of reference if somebody measure it from here by some experimental arrangement. So this T will be equal T naught. This is our T naught. Okay. So T naught is like when this formula 1 minus V square by C square, and you just see, look, that the t naught is 12 second, and let us see that what it will be looking like, that 1 minus that the v square, so that is zero point 0.6 c, so zero point 0.6 c and c will get cancelled, and you have will be having this equation. Let me pick a calculator and let me calculate this value, that how it will look like. So see here that it will be 1, and here it will be 1 minus zero point 0.6 square. So that time will came out to be log, that will be came out to be 15 seconds. This is what, 15 seconds. So look, you have seen that the time is dilated here. The time is what? The time is dilated here. So that is now you can calculate that how much it is now slower, that how much 1 second is bigger on the what, bigger on the moving frame of reference. So this all happens for the frame of references which are moving with a speed equal to zero point 0.6 c. Very sorry. That is, which is equal to, for the speed which nearly equal to the speed of light, right? For example, f the bodies which are very slow, for that is for ordinary bodies, for slow bodies, for ordinary speed or for slow speed. So look, for example, when the speed is very, very less than what the speed of light, then what will happen? We will take v nearly equal 0. And what will happen? T will become equal to T naught into 1 minus 0. And what does this means? That T will equals T naught, that the relativistic, that is the relativistic time will equal to the non relativistic time, the non relativistic time. This will excuse me, I'm just doing. So there is no relativistic effect at the so what is this result? The result is that there is relativistic no relativistic effect at very low speed, at very low speed. And the time dilation is experimentally proved. It is now experimental fact, and you can see how it is experimentally verified, right? So you can study that experiment. Now when the objects, another case, for example, when the v equals c, that is that if the objects moves with the speed of light, then what will happen? Then t will become equal t naught, and your this equation is, it will become v square by c square will become t naught into 1 minus 1. And because if v is equal to c, and what happens, that it will become t. So that is the time infinitely large, and what is the result? That time will frozen, time will time will freeze, it will comes to stop, right? So that is how we, the scientists, talk about the time dilation, or the going into the future, right? So this is how the time dilation is, though right now it is not possible, because no material particle can travel with the speed of light, right? So but this is just what the experimental arrangement is. The point B is the length contraction. The length contraction. that the length of an object, the length decreases, right? But remember, in the direction of motion, the length contracted in the direction of motion, in the direction of motion. Now, class, I'm sorry, let me explain this thing to you, because you'll be thinking, why is it this happen, right? So though there is no proof in your book or like that, but I want to explain it to you. It is because, for example, let us suppose that if there is what, the two mirrors, right? And the two mirrors are fitted into the frame of reference, inertial frame of reference. Let me explain this to you. See here, in this inertial frame of reference, if the light signals travel between these two mirrors, so they are forward or moving ahead at the same distance, so the light will take the same time here. That is what we call t naught time. Okay, they will take the same time here. If the observer, if there is an observer measuring this time between, that is this mirror M and this mirror M1, and this is mirror M2, and you know S is equal to what? S is equal to V into T, and T is equal to S by V. So for C, this is equal to S by C. This distance is considered to be the distance S, right? And the observer measure the time t. Now if there is another observer, let's say, and if he measure this time, then for him the situation is different. Why? Because the, for example, if at one point like this, for him the light travel at, look, if it is here now, if it is here now, and if it is here, here the for the moving. So look, this is for the first stick, but for the second stick, as I told, the light, as the observer is moving in this frame of reference, then the light that carry information, that is the light signal, will now just moving this way and then this way, like this, and you will just make this sort of arrangement. So you see, this is the speed of light, this is this distance, this distance, and this distance. So this distance is longer, and this distance is what? This distance is shorter, right? So to travel the, for the light to that is, that since the speed of light is what? Since the speed of light is constant, it is what? It is constant, or it is the same for all the observer. But here you see that the distance is definitely greater. So if the distance is greater, so in order to gain the same speed, c is equal to what? Uh, uh, S is equal to S by T. So S by T. So in order to keep the speed constant, so if the distance is longer, we cannot do anything with the distance right now. So what will happen? Time must be dilated. If the distance increases, time must increase to keep the speed of light constant, right? So this is what it results, right? So it is because of this effect that there is what? That the time is dilated to keep the speed of light constant. Why? Because it is universal fact. Similarly, for the length contraction, what happens for the length contraction? That L is equal to L naught into, this is 1 minus v square by c square. Here the time dilation is because of the fact that is, here look, in this situation here, what you notice that is the factor, this is sometimes called gamma, v square by c square equals gamma. So this gamma here in this case is 1 over gamma is less than 1, therefore t will be greater than t naught. Here this situation is different. This is what, now I will not explain again to you that this is relativistic length and this is non-relativistic length, and I explain all the term in the same theory and the same explanation applicable here also. But now as in this case, what you see is the gamma, which I told 1 minus v square by c square under the root, it is less than 1. So this implies here that L must be less than L naught, right? That when you multiply a number with a smaller number, it will make it small, right? Or smaller means which is in a fraction, right? So here you see that the result is what? The result is the length contraction, the length contraction, that length contracted in the direction of motion. Okay, so this is the another example of the length contraction. So the 2 points, inshallah, the time dilation, sorry, the mass increment, the mass increment and the energy equivalence. The energy equivalence I did not mention, I think, here. So the mass increment and the energy equivalent, inshallah, I will explain to you in my next lecture. So for this, you can just look for many other experiment which can explain to you the length contraction, but I explain the time dilation in a greater detail. The same explanation are applicable here also, that length contract in the direction of motion for an object which moves relative to the speed of light. And when an object moves with the speed of light, then the factor v square c square will become 1 and the length will become 0. So what does this means? That the object nearly cease to exist, right? And when at low speed, the relativistic length will become equal to the non-relativistic length, right? And there will be no relativistic effect observed for low speed objects in the direction of motion. So this is the end of the lecture today. So inshallah, you have learned from our today lecture.